Welcome to Brain Vision.
In this problem, we're asked to calculate the half-life for 1 gram of samarium-147 isotope that undergoes alpha decay. I wrote out the reaction here. We have samarium-147 that decays into a daughter element of some sort that has atomic mass number 143 and atomic number 60, and the other decay product is the alpha particle. And an alpha particle has an atomic mass unit of 4 and an atomic number of 2, and it is a helium. It's a helium nucleus. So the other information given in this problem is that the activity of the samarium-147 decays at a rate of 120 decays per second. And we're also given that the abundance of samarium is about 15%. So the first step of this problem, we can figure out two of the constants that are needed in order to solve for these half-life, given the relationship that activity is the product of the decay constant lambda times the number of nuclei present, n. Given this relation, we can find out lambda as the proportion of activity to number of nuclei present. But we don't have the number n yet, so we'll need to determine that from the atomic mass of samarium-147. Well, we know that the atomic mass is roughly equal to the atomic mass number of an element. We can use that in a to figure out the number of nuclei present, or the number of atoms present of samarium-147 as follows. We can enter in our 15% abundance times the 1 gram that we're asked to solve for. Both were pieces of information given in the problem. And divide that, this amount, this mass of samarium-147 in the numerator, divide that by the atomic mass of samarium-147, which is roughly equal to 147 atomic mass units, and as well as dividing this mass by the grams to atomic mass unit conversion factor of 1.66 times 10 to the negative 24th. Doing that, we find we have a that there are 6.15 times 10 to the 20th nuclei present in the sample. So dividing this figure, we can rather do the division. Now that we have a figure for n, we can divide into the activity value we were given of 120 decays per second. Divide that value of r by our 6.15 times 10 to the 20th nuclei. And we get a value of 1.95 times 10 to the negative 19th. And that is the decay rate in, the decay constant in units of reciprocal seconds. Now that we have the decay constant, we can use that to solve for the half-life in seconds of our of samarium 147. We know that because we have the relation of half-life to decay constant of natural log of 2 divided by the half-life in seconds. So we can rearrange our factors in this and divide the numerical approximation of logarithm 2 by our lambda that we solved for in the previous step. Doing this, we find that the half-life in seconds of our sample is 3.55 times 10 to the 18th. Seconds. That is a big number, so it'd probably be a little bit less unwieldy for us to convert it to years. To convert seconds into years, we have to find out how many seconds there are in a year and divide by that number. I do it as follows. There are 365 days in a year, and there are 86,400 seconds in a day. So doing this division, we find that we are left with 1.1 times 10 to the 11th years for the half-life of samarium 147. And that's our answer.